Good day everyone, welcome to chapter 36. In this chapter, we will explore how light behaves when it passes through openings or around the obstacles, building on what we learned about wave optics and interference. Diffraction is a key phenomenon that reveals the wave nature of light, and it has important applications in science and technology. Here are main learning goals for this chapter. First, we'll look at what happens when light encounters a sharp edge or a small opening, something geometric optics can't fully explain with this. So then, we'll dive deep into the single-slit diffraction, how it forms, how to describe the pattern mathematically, and how intensity is distributed. Next, we'll move to multiple slits, which lead us to diffraction gratings. So, some devices used to separate light into its component wavelengths. We are also explore X-ray diffraction, which let us study the atomic structure of the crystals. So, finally, we'll discuss how diffraction limits how clearly we can see details with the telescopes and other optical instruments. Let's start with two interesting questions you might have wondered about. First, have you ever noticed that rainbow colors reflected from a CD, DVD, or Blu-ray disc? These colors come from diffraction, so coherent light interacting with the tiny, closely spaced bits on the surface. Second, if you shine light from a small point source onto a sharp object like a razor blade, you won't see a perfectly sharp shadow. Instead, you will see a faint, bright, and dark fringes right at the edge. Both examples show that light does not always travel in straight lines, as geometric optics suggests. So this chapter continues our study of light as a wave, and we also learn how diffraction makes a hologram possible. So those amazing 3D images that look like a real object. Geometric optics teaches us that light travels in straight lines. So if you put an object between a point light source and a screen, you should get a perfectly sharp shadow with a clear boundary between the light and dark. But in reality, that's not what happens. Instead, the light bends slightly around the edges of the object, creating a pattern of bright and dark bands right where the shadow should be sharp. So this bending and spreading of light as it passes through openings or around obstacles is called diffraction. It is a fundamental property of all waves, water waves, sound waves, and light waves all diffract. We use Huygens principle to explain and analyze the diffraction. Remember, Huygens principle says every point on a wavefront acts as a source of a tiny secondary wavelets, and the new wavefront is the sum of all of these wavelets. So when these wavelets overlap, they interfere constructively or destructively to create a diffraction patterns. So there are two main types of diffraction. First is the Fresnel diffraction. So this happens when the light source or the obstacle and the screen are all close together. So the math here is more complex because the light rays are not parallel. While on the other hand, the Fraunhofer diffraction, this is the simpler case where the source and the screen are very far away, or we use lenses to make the light rays a parallel. So this is what we all focus in our calculations. Now let's look at what happens when light passes through a narrow single slit. Geometric optics predict we should just see one bright line on the screen, exactly the same width as the slit itself, but again, reality is different. Instead, we see a central bright maximum that is much wider than the slit, with smaller, dimmer bright fringes on either the side. But one very important rule is the narrower the slit, the more the light spreads out, and the wider the diffraction pattern becomes. So if the slit is extremely narrow, about the same size as the wavelength of the light, almost all the light spreads out into one very broad central band. So this is the opposite of what you might expect. Making the opening smaller makes the light spread more. This diagram shows the difference between the two types of a single slit diffraction we mentioned earlier. In a part A, we divide the slit itself into many tiny strips. Each strip is a source of a Huygens wavelets. For the part B, Fresnel diffraction's screen is closed, so the light rays from different parts of the slit to a point on the screen are not parallel, so the path differences are complicated. For part C, Fraunhofer diffraction screen is very far away. Now, the rays are nearly parallel, which makes the math much easier. For the part D, we can use a converging lens to create a Fraunhofer pattern even on a nearby screen. The lens focuses parallel rays to a point, so that the result is exactly the same as if the screen were infinitely far away. This is the setup we use in our lab experiments. Now, let's find exactly where the dark fringes occur. So we can do this by dividing the slit into two equal halves. For every point in the top half, there is a corresponding point in the bottom half. So the path difference between these pairs of rays reaching a point on the screen is A over 2 sine theta. So when this path difference equals to the wavelength over 2, the waves from these 2 points arrive exactly out of phase and cancel each other completely. So this happens for all such pairs across the whole slit. So the result is total darkness, a dark fringe. So this leads us to the condition for the dark fringes. A sine theta is equal to m wavelength. So if theta is very small, which it usually is, so we can use the approximation of a sine theta, tan theta is equal to theta. So then the distance from the center of the pattern to the MTH dark fringe is ym is equal to x times m wavelength over A. So this formula shows that the longer wavelengths or the red light produce wider patterns, and the narrower slits produce a wider patterns. So fringes are equally spaced for all small angles. So let's apply what we just learned with the example 36.1. We have red laser light with a wavelength is equal to 633 nanometers. Then it passes through a single slit and forms a pattern on a screen. X is equal to 6.0 meters away. So we measure the distance from the bright center to the first dark fringe. Y1 is equal to 32 millimeters. So we need to find the width A of the slit. So using this formula, so after using our formula, we rearrange to solve for A and easily plug in the numbers. So the slit is about 0.12 millimeters wide, very in as expected. So this example shows us how we can use the diffraction measurements to find the very small sizes. So far, we've only talked about where the dark fringes are. Now we'll look at how bright the light is at different points, which is the intensity distribution. We use phasors to calculate this. Each tiny strip in the slit contributes a small electric field vector, or the phasor. So here, at the center of the theta is equal to 0 degree, all wavelets travel the same distance, so they are all in phase. So the phasors line up straight and their sum is maximum. This is the bright central maximum. Moving away from center, wavelets from different parts of the slit have different path lengths, so they arrive with different phases. The phasors form an arc. The resultant vector here is shorter, so intensity is lower. At the dark fringe, the phasors form a complete closed circle, or sum is 0. But between minima, partial cancellation gives smaller secondary bright fringes much dimmer than the center. So we define beta as the total phase difference between the wavelet from the very top of the slit and the one from the very bottom is beta is equal to 2 pi over wavelength A sine theta. This animation shows exactly how the pattern builds up as we move from the center outward. Each blue arrow represents the electric field contribution from one part of the slit. At the center, all arrows point the same way. Strong total field, bright light. So as we move sideways, the arrow twists around because of the phase differences. So the green arrows shows the total strength. Where the arrows make a full circle, the total is 0, which is equivalent to the dark fringe. So between those points, the green arrow is shorter than the center, so brightness is lower. Well, the red line is the component that actually determines the intensity we see, and the cyan curve traces the final intensity pattern. Notice how tall and wide the central peak is, and how quickly the smaller peaks fade away. From the phasor diagram, we can derive the exact formula for intensity. The phasors lie along the arc of the circle. The arc length is the maximum field, and the angle subtended is beta. So the radius of the circle is this. So the resultant field is the chord length of the arc. Since intensity is proportional to the square of the electric field, this is the famous sinc squared function. It perfectly describes the single-slit pattern. The maximum at the beta is equal to 0. Zero intensity whenever beta is a multiple of 2 pi, which matches our dark fringe condition, and the smaller peaks in between. Here's what the intensity graph looks like. So you can see the huge central peak. This is why the center is so bright. The secondary maxima are much dimmer, only about 4.7% of the central brightness for the first one and less than 2% for the second. So the bright spots are not exactly halfway between the dark spots. We find their positions mathematically by taking the derivative of the intensity formula and setting it to 0. So the result is slightly offset, but for most purposes, the difference is a quick small. Also notice that the central peak is exactly twice as wide as the side peaks. So that's a key feature of a single-slit diffraction. So the shape of diffraction pattern depends entirely on the ratio of the slit with A to the wavelength of the light. So if A is into a wavelength, light spreads out so much you only see one wide fuzzy bright spot. But if A is several times with a wavelength, you'll see a clear fringes with a noticeable central width. But if A is greater than the wavelength, diffraction effects are very small and light behave most like straight lines in a geometrical optics. So, example here in 36.2 shows how to use the intensity formula. So, as you can see, below here is the equation of the intensity. But what happens when we have more than 2 slits? So let's say n slits all equally spaced. So the condition for bright maxima is still the same. D sine theta is equal to m wavelength. But the pattern changes dramatically. So we use the phasors again, now with n arrows, one from each slit at a maximum. All phasors point the same way, adding up to a very strong total field between the maxima. So the phasors curl around and cancel out completely, creating many sharp and dark gaps. So the key rule here is as n increases, the bright maxima stay in the same positions, maxima become much narrower and brighter, dark regions between them become wider and darker. So this is the principle behind the diffraction grating. So in chapter 35, we studied 2 slit interference, but we assumed that the slits were infinitely narrow. In reality, slits have a width, so both the interference and diffraction happens at the same time. The final pattern is the product of the two things. First is the interference patterns from light coming from two different slits, many fine, equally spaced, bright fringes. Second, the diffraction pattern from each individual slit, a broad, bright central band with a dimmer side bands. So think of diffraction as an envelope that controls how bright the interference fringes can be. So inside the central diffraction peak, interference fringes are bright. Outside, they fade away. So a key effect here is, so if the slit separation D is an integer multiple of the slit with A, some interference maxima will line up exactly with the diffraction minima. Here is a visual comparison of the patterns for 2, 8, and 16 slits. With 2 slits, bright fringes are wide and fuzzy. With 8 slits, fringes get thin and sharp. While with 16 slits, fringes are extremely sharp and bright. Because the bright lines are so narrow, we can tell very precisely with which angle a certain wavelength appears at. So if we shine white light which has all colors into many slits, each wavelength bends to a slightly different angle. This separates the light into a rainbow spectrum. So different values of M give different rainbows. M is equal to 0 is straight ahead, all colors overlap to white. M is equal to 1, 2, 3, spread out the colors further and further apart. A diffraction grating is a device with hundreds or thousands of slits per millimeter. It works exactly like the multi-slit patterns we just discussed earlier, but with n very large, the result is extremely sharp, bright spectral lines. Example here in 36.4, we have a grating with 600 slits per millimeter. First is we find the slit separation, which D is equal to 1 millimeter over 600 is equal to 1.667 times 10 to the power of negative 6 meter. For meter is equal to 1. So for the first order spectrum spans from 13.2 degrees to 26.7 degree. For part B, we calculate the ranges from m is equal to 2 and m is equal to 3. So we find the second and third orders to overlap. The red of m is equal to 2 is at a large angle that violet of m is equal to 3. So this is an important practical consideration when using the gratings. The main use of diffraction gratings is in spectroscopy, studying the light emitted or absorbed by objects. A grating spectrograph spreads light out into its component wavelengths, producing a spectrum. So why use a grating instead of a prism? So gratings work for all wavelengths, visible, ultraviolet, X-ray, and etc. So we can control the amount of spread by changing the slit spacing. The more slits, the sharper the lines, and the better we can tell two very similar wavelengths apart. So this diagram shows the sun on the left, just white light on the right, spread into a full rainbow spectrum with dark lines. So these lines tell us exactly what elements are in the sun's atmosphere. This diagram shows how modern astronomical grating spectrograph works. Light from a telescope is sent through optical fibers, then shaped into a beam of parallel rays. It hits the diffraction grating, which sends different colors in different directions. So mirrors and lenses focuses each color to a precise position on a digital camera or detector. So by analyzing the exact position and brightness of each spectral line, astronomers can find the chemical composition, temperature, speed, and distance of stars and galaxies, all from the light they send us. Visible light wavelengths are hundreds of nanometers, which is too big to diffract off individual atoms. But X-rays have wavelengths around 0.1 nanometers, which is about the same as the distance between the atoms in a crystal. So when X-rays pass through a crystal, the regular rows of atoms act like a three-dimensional diffraction grating. So the X-rays scatter off the atoms and the scattered waves interfere. So the result is a pattern of bright spots called a Lu pattern, recorded on film or detector. So from this pattern, scientists can work out exactly how the atoms are arranged inside the crystal. So this is how we first discovered the structure of DNA and how design new materials today. The K law for X-ray diffraction is the Bragg condition, discovered by William and Lawrence Bragg. Think of the crystal as made of many parallel layers of atoms separated by distance. X-rays reflect off these layers. For the reflections to add up constructively bright spot, the path difference between rays reflecting off different layers must be a whole number of the wavelengths. 2D sine theta is equal to m wavelength. So the factor of 2 comes from the fact that the ray traveled down to one layer and back up again. By measuring the angles where bright spots appear, we can solve for the spacing between atoms. This is the foundation of the X-ray crystallography used in chemistry, biology, and physics. So far, we've talked about slits. What about a round opening like the lens in a telescope or the pupil of your eye? It also diffracts light, but the pattern is in a circular motion. So you get a bright central spot called the airy disk, surrounded by the fainter, concentric bright and dark rings. So the angle to the first dark ring is given by sine theta 1 is equal to 1.22 wavelength over d. Notice the 1.22 factor, it comes from the circular geometry. So this formula is extremely important because it tells us the smallest spot size a lens can make. No matter how perfect your lens is, diffraction will always blur the image a little bit. Diffraction sets a fundamental limit to how fine detail we can see. This is called the diffraction limit. Imagine looking at two tiny stars close together. Each star produces its own airy disk pattern. So if the disks are big and overlap too much, you see just one blob, you can tell them apart. But if the disks are small enough, you can see two separate spots. The Rayleigh criterion says two sources are just resolvable when the center of one airy disk falls exactly on the first dark ring of the other. This happens when their angular separation is greater than 1.22 wavelength over d. So to get better resolution or the sharper images, we need a larger aperture. That's why telescopes have huge mirrors and why microscopes use a oil immersion to reduce the effective wavelength. This is why astronomers build such big telescopes. The Very Large Array or the VLA in the New Mexico is made of many radio dishes acting together as one huge aperture. So this gives it the resolving power to see incredibly fine details in distant galaxies. Example in 36.6 in our book walks through the calculation how big does a telescope need to see a certain detail on a planet. Using theta is equal to 122 wavelength over d, we can find the larger diameter always means better vision. Diffraction is the ultimate limit. Nothing can beat, but we can make it as small possible by using a big aperture and short wavelengths. Finally, let's look at one amazing application of diffraction, which is the holography. Unlike a normal photo, which just records the brightness, a hologram records the complete wavefront of light coming from an object. So how it's made? So first, it split a laser beam into two parts. Second, object beam illuminates the object reflects onto the film. Third, reference beam goes directly to film. Fourth, where they meet, they interfere, creating a microscopic diffraction patterns on the film. So, when we see a shine light back through this developed film, it diffracts exactly like the original object did. Your eye sees a perfect 3D replica that changes perfect perspective as you move your head. This diagram explains the process step by step. During recording, the object wave is curved and complex. The reference wave is flat. Their interference creates a pattern of fine, wiggly lines on the film, essentially a very complicated diffraction grating. During viewing, you shine a light similar to a reference beam through the film. The pattern diffracts the light exactly the way the object scattered it before. The result, your brain interprets the diffracted light as coming from a real 3D object floating in the space. Holography works because diffraction preserves both the amplitude and phase of the light wave, something no ordinary photo can do. Here is the proof. These two photos show the same hologram, taken from two different viewpoints. Notice how you see different parts of the object, and how foreground and background shift relative to each other. So just like you would see with a real physical object. That's the magic of the holography, made possible entirely by diffraction and interference.